Right, so this section has been like, I'm actually kind of behind on differential equations because last week was so hectic, but this, just doing the homeworks online, this has been like, this and 4.6 have been really difficult conceptually. I can't, change of base is so weird. Anyway, so an important reason for specifying a basis B for a vector space V is to impose a coordinate system. This section will show that if B contains n vectors, then the coordinate system will make V act like Rn. If V is already Rn itself, then B will determine a coordinate system that gives a new view of V. The existence of coordinate systems rests on the following fundamental result. Let B equal B1 to Bn be a basis for a vector space V. Then for each x in V, there exists a unique set of scalars C1 to Cn such that the linear combination of C and B is x. The proof is, since B spans V, there exist scalars such that one holds. Suppose x also has the representation d1 to dn. Then subtracting, we have 0 equal to x minus x is equal to c1, etc. Since B is linearly independent, the weights must all be 0. That is Cj equals Cd. Okay, great. Or Cj equals Dj. Okay, now another definition. All right, suppose B equal to B1 to Bn is a basis for V and x is in V. The coordinates of x relative to the basis B, otherwise known as the B coordinates of x, are the weights C1 to Cn such that x is equal to C1, the linear combination of C and B. Okay, so this is that x under the basis notation. So it's, if you have a basis B and you treat it like a matrix, then you get x, or B times xB is equal to x. Okay, so this is called the coordinate vector of x relative to B, or the B coordinate vector of x. Okay, consider a basis B for R2. Suppose that x in R2 is the coordinate vector. Find x. So what you're going to do here is just do the matrix multiplication, or the minus 2 times B1 plus 3 times B2. Okay, the entries in the vector x are the coordinates of x relative to the standard basis. A graphical interpretation of coordinates. A coordinate system on a set consists of a one-to-one mapping of the points in the set into Rn. For example, ordinary graph paper provides a coordinate system for the plane when one selects perpendicular axes and a unit of measurement on each axis. Figure 2 shows the vectors b1 and b2 and x from geometrically. Vectors lie on a vertical line in both figures. However, the standard coordinate grid Yeah, that's weird. So you can, x really never moves relative to 0, but which makes sense. I mean, it'd be weird if it did, but also the whole grid has changed. In crystallography, the description of a crystal lattice is aided by choosing a basis UVW for R3 that corresponds to 3 adjacent edges for a unit cell of the crystal. That's interesting. When B basis for Rn is fixed, the B coordinate vector of x is easily found of a specified x. If you have x and you're trying to find the B coordinate vector for it, it requires a linear solve, right? So you let B1 and B2 be the basis vectors, x equals a 4, 5. Find the coordinate vector xb of x relative to B. So you need to do a linear solve. Okay. The matrix in 3 changes the B coordinates of a vector x into the standard coordinates for x. An analogous change of coordinates can be carried out in Rn for a basis B1 to Bn. We call PB the change of coordinates matrix from B to the standard basis. Left multiplication by PB transforms the coordinate vector into x. The change of coordinates equation in 4 is important and will be needed at several points in chapters 5 and 7. Since the columns of PB form a basis for Rn, PB is invertible. Left multiplication by P inverse converts x into its B coordinate vector. The correspondence x to xb produced here by P inverse is the coordinate mapping mentioned earlier. Since P inverse is an invertible matrix, the coordinate mapping is a one-to-one linear transformation from Rn onto Rn. This property of the coordinate mapping is also true in a general vector space that has a basis. Okay, the coordinate mapping. Choosing a basis B for a vector space V introduces a coordinate system in V. The coordinate mapping connects the possibly unfamiliar space V to the familiar space Rn. I don't really understand that. The figure 5, okay. Points in V can now be identified by their new names. B is a basis for V, then the coordinate mapping x to x from x to the coordinate vector of x relative to B is a one-to-one linear transformation from V onto Rn. Okay, take two vectors in V, then using vector operations, it follows that right. Basically, you have coordinates relative to a basis, and you always do. You're always talking relative to some basis. It just so happens that there's one basis that's way better than everyone else. Okay, so they show that coordinate mapping is linear transformation. The linearity of the coordinate mapping extends to linear combinations. Okay, yeah, that's obvious. All right. The coordinate mapping in Theorem 9 is an important example of an isomorphism from V onto Rn. In general, a one-to-one linear transformation from a vector space V onto a vector space W is called an isomorphism from W onto V. One-to-one and onto, then it's the notation and terminology for V and W may differ, but the two spaces are indistinguishable as vector spaces. Every vector space calculation in V is accurately reproduced in W and vice versa. In particular, any real vector space with a basis of n vectors is indistinguishable from Rn. Okay. Let B be the standard basis of P3 of polynomials, that is, this basis. The typical element of P has the form this. Since P is already displayed as a linear combination of the standard basis vectors, we conclude that the coordinate mapping from P to PB, okay, is an isomorphism from P3 onto R4. All vector space operations in P3 correspond to operations in R4. If we think of P3 and R4 as displays on two computer screens connected via their coordinate mapping, then every vector space operation in P3 on one screen is exactly duplicated by a... I love that they did this analogy because it's so unnecessary. The vectors on the P3 look different from those on the R4 screen, but they act as vectors in exactly the same way. Okay, example 6. Use coordinate vectors to verify that the polynomials 1 plus 2t, 4 plus t, all right, and 3 plus 2t are linearly dependent. The coordinate mapping produces, from example 5, produces the coordinate vectors 1, 0, 2, respectively. Writing these vectors as the columns for matrix A, we can determine their independence by row reducing the augmented matrix. The columns of A are linearly dependent. In fact, it's easy to check that column 3 of A is 2 times column 2 minus 5 times column 1. Okay. The final example concerns a plane in R3 that is isomorphic to R2. And B is a basis for H equal to the span of V1 and V2. Determine if X is in H, and if it is, find the coordinate vector of X relative to B. Okay. Okay, so they make the augmented, then they row reduce, then they find that this. Right. Okay, and that solution is under the, yeah. So XB is just equal to the linear solve. Right. It's interesting to think of these as a basis of a coordinate system. It's kind of an interesting way to think about it. If a different basis for H were chosen, would the associated coordinate system also make If a different basis for H was chosen, would the associated coordinate system also make H isomorphic to R2? Surely this must be true. We'll prove it in the next section. All right. Okay, so first we need to show that the set... All right, so clearly it is because it's in echelon form, and since it's in echelon form, there's no way that you could write this in terms of the other ones, or... Okay, the change of... Okay, so A, we said yes, and we showed it easily, because it's in echelon form, and all the it has 3 pivots on the diagonal. Or, it has 3 pivots, and they're all on the diagonal. Okay, find the change of coordinates matrix from B to the standard basis. Oh, see, this is where I get so confused, because is this... Presumably, this is just the matrix formed by these columns. So this is going to be this matrix times xb is equal to x. Alternatively, you could take the inverse of this. Okay, the second one, the set B is a basis for P2. Find the coordinate vector relative to B. So, okay. All right, I'll do these. So we have I'm not going to do this one, but I am going to do 2. So let's do 2. Oh. All right. So for problem 2, we have B is equal to 1 plus t, 1 plus t squared, t plus t squared. Basis of P2. Or, okay, so first off, to write this in the standard basis or whatever, it's going to be P is equal to 6, 3, minus 1. Okay, and then our basis B as a matrix is going to be equal to 1, 1, 0, 1, 0, 1, 0, 1, 1. Okay, so now what we want to find is B, P, B is equal to P. So now we just need to do B backslash P. So if we want that, we can just do this. So we have B is equal to 1, 1, 0, 1, 0, 1, 0, 1, 1. P is equal to 6, 3, minus 1. Oh, wait, I need commas. Actually, is that a real thing? Characteristic? No, they don't even have a thing. All right. So now all we have to do is B backslash P. And we would get that P relative to the basis B is equal to 5, 1, minus 2. All right. So let's check if we were right. It's row equivalent to the identity matrix. Therefore, it's invertible and its columns form a basis. Part A, the change of coordinates matrix is this. Is that just the columns of it? 3, 6, 3? Yeah. Okay. So then this is the equation. That's what I was thinking. Then to solve it's probably easier to row reduce the matrix than to compute. Yeah, you just row reduce. That's fine. 1 1 1 0 1 0 1 1 5 1 minus 2. Yep. Great. All right, now let's read through all the problems and we'll mark down some to do. Because I remember these two sections I struggled a lot with. Okay. So in exercise 1 to 4, find the vector x determined by the given coordinate vector xb. Okay, so this one's easy because it's literally just going to be matrix vector multiplication. So we're not going to do any of those because it's literally just multiply the two numbers or the two things. In exercises 5 through 8, find the coordinate vector xb of x relative to the given basis. Okay, so then this is going to be just backslashes. So maybe we'll do just like 5 and 7. Like, why not? All right. In exercises 9 and 10, find the change of coordinates matrix from B to the standard basis. Okay, we'll do 9. Actually, is there answers at the end of this book? Oh, there are. I never realized that. That's so sick. Okay. All right. 11 and 12, use an inverse matrix to find xb for the given x and b. Okay, we'll do 11. I'm down with that. The set is a basis for P2. Find the coordinate vector relative to B. Okay, that one's easy, but we'll do that one. All right, true falses 15 through 20. So we'll do 15 through 20. Okay, this section might be pretty fast. It's always the tail that's long. All right, span R2 but do not form a basis. Find two different ways to express 1, 1 as a linear combination of... Okay, we'll do that one. I wonder what... Yeah, all right. Okay, let B be a basis for a vector space V. Explain why the B coordinate vectors are the columns. Explain why the B coordinate vectors are the columns of the identity matrix. Okay, that's a good one. I think it's because explain why the B coordinate vectors of the basis elements are the columns. So, all right, so we'll do that. That's a good one. I like that one. Okay, let S be a finite set in a vector space V with the property that every x in V has a unique representation as a linear has a unique representation as a linear combination of the elements of X. Show that S is a basis. Okay. 23 seems good. How do you do it? So it has a unique representation. That means it's onto, or it's onto because every, and it's one-to-one because the action of the mapping implies that if two elements under the mapping are equal, then the elements themselves were equal. So if it's one-to-one and onto, it's a basis. I don't know. We'll do a double check on that. All right. Suppose V1 of V4 is a linearly dependent spanning set for a vector space V. Show that each W in V can be expressed in more than one way. All right, that's a good one. It's a little bit of a review, I feel like, but that's a good one. I mean, what I think you do is you show you let some arbitrary symbolic linear combination of V1 to V3 equal V4, and then you just like plug in, and then you can probably just choose. Yeah, that's that. Okay. Let B equal, since the coordinate mapping of since the coordinate mapping determined by B is a linear transformation from R2 into R2. Okay, 25 is good. It's just going to be B inverse, but still, if it's fast, it's just worth doing for the repetition. All right, 26. Let B, basis for Rn, produce a description. I feel like it's just going to be B inverse again. It's going to be take these, yeah, as the, okay, anyways. All right, exercises 27 through 30 concern a vector space V and a basis B and the coordinate mapping from X to X relative to B. Show that the coordinate mapping is 1-to-1. So you suppose that U relative to B and W relative to B are equal for some U and W in V, and show that U is equal to W. All right, 27 is pretty good. I guess what you want to do is that you say given U and W, you have some matrix P inverse, P inverse that maps U to U relative to B and W, it maps something to itself relative to B, like this. Then you suppose that that U and W are not equal, but that this is equal, but then you apply P to both sides, and then you find that U must be W. Okay, so that one should be pretty easy. I think it's just applying the reverse coordinate transformation. Hey, what's up? Okay, 28, show that the coordinate mapping is onto. Okay, to show that it's onto, so you take some arbitrary element y in Rn, and is this not, okay, 27 and 28 are going to be good problems. What was 26? All right, 26, 27, 28. Okay, so 29 is show that a subset U1 to UP is linearly in V is linearly independent if and only if the set of coordinate vectors is linearly independent in Rn. Okay, so 29 actually seems really good. Given vectors U1 to UP and W and V, show that W is a linear combination. Right. This pretty interesting. I'll do 30. We'll see how much of this we actually get to, but I feel like it's always useful just to read all the problems. In 31 to 34, use coordinate vectors to test the linear independence of the sets of polynomials. All right, I'll do 31. Use coordinate vectors to test whether the following sets of polynomials span. Okay. 35, I feel like we can skip. 35 is just amounts to you put this as a matrix. And then you row reduce it or something. And you just test the rank of it. As long as the rank is 2 or 3. Okay, 36. All right. So let's just get started then. So we're starting with, so let me just write these down so I don't keep losing them. Oh, wow. That's so interesting. Okay. All right. So what did I say? 5, 7, 9, 11, 13, 15, 15 through 30, or 31. And that's it. That's what we're doing. All right. But we're probably not going to actually do all those. Okay. So 5, this is just going to be an inverse solve. So let me just write it down on paper, but then I'm going to solve it on the computer. 1, 2, minus 2, minus 3, minus 5, 1. All right, so we're just going to do A is equal to 1, 2, minus 3, minus 5, A backslash minus 2, 1. All right, so then that means that X relative to B is equal to 8 and 5, minus 5. Okay, so that's pretty cool. All right, so 7. 7 is 1 minus 3, 2, minus 1, 4, minus 2, minus 3, 9, and 4. And x is equal to 8 minus 9 and 6. All right. Eight minus 9 and 6. Okay, so then xb is equal to minus 1, minus 1, 3. So then what that means is that if I did let's say this is, then if I did xa times xb, I should get x. 8 minus 9 and 6, yeah. All right, problem 9. Let's just make sure that we got these right. So 5 is correct, 7 is correct. Now 9 should just be those columns, right? 2, 1, minus 9, 8. Okay, so then we don't need to do 11. I don't know why I wrote 11. Oh, because 11 is a different one. All right, use an inverse matrix to find xb. All right, so if we have for 11, 3 minus 4 minus 5, 6, and then x is equal to 2 minus 6, then we're just going to, I know Rust, I know Python, I know Julia. Once you know one, you kind of know them all. I mean, they're all more or less pretty much the same. I mean, more or less. I mean, there's broad categories, but like the whole idea is the same. Okay, a is equal to 3 minus 4 minus 5, 6. Now, real programmers, bro, we just synthesize we just synthesize the Turing machines in our mind, and we just write down the table for the Turing machine. I don't even program, bro. I just write in Turing machines. And if I find that it's a regular language, I just write the DFA. I can just synthesize it from my mind. Okay, so wait, what are we trying to find? We're just trying to find inv A times X. Okay, so this is going to be XB. The difference between first order and second order, in differential equations, the difference between first order and second order is to what, like the highest differential is. So if you have like y double prime, that's a second order. So like the harmonic oscillator, for instance, is a second order differential equation. Wait, so let's just make sure that we had it right. What was it? 6 and 4. Yep. Okay, good. Are we doing 13? Yeah, we're doing 13. Okay, these are fun, and I don't know why I think they're fun, because they're actually lame, but I find them fun. There's just something about the fact that it's like a different vector space. You know, these vector space of polynomials it's just more fun. All right, so we're gonna write out the matrix. It's gonna be, or we could just, yeah, okay, I'll just write it down here. So it's gonna be 1, 0, 1, 0, 1, 1, and then 1, 2, 1. Okay, and then our x is gonna be 1, 4, and 7. I've never seen a fourth. Where are you seeing that? I've never seen fourth order. Oh yeah, you can do as many orders as you want. I've never seen it in real life, but you can do 30. You can do 1,000. Okay, wait. I just need to write this down. So this is gonna be a is equal to 1, 0, 1, 0, 1, 2, 1, 1, 1. Okay, then P, or let's just call it X. X is equal to 1, 4, 7. Okay, so now, what was the problem? It's find P relative to find X, B. It's going to be equal to A backslash X. Most of this stuff in linear algebra, it's literally just doing a linear solve. It's just different ways to write it. But all of it just comes down to linear solve. So 13 was 2, 6 minus 1. 2, 6 minus 1. All right. Oh, yeah. I don't remember why I... Oh, yeah. I was trying to look at what the matrix form of a high order ODE is. And it's not what I thought it was. It was something different. But that's the... Yeah, I was just looking at what the structure of the matrix is. Okay, 15. All right, true falses. If X is in V and B contains n vectors. Okay, so unless otherwise stated, B is a basis. Okay, unless otherwise stated, B is a base. Then the B coordinate vector. That is true. Okay, 16. If B is the standard basis, then the B coordinate of an X in Rn is X itself. That's true as well. Because then the basis matrix is just going to be the identity matrix. So it doesn't actually change anything. If PB is the change of coordinates matrix, then XB is equal to... That's false. That's false. That's going to change the standard basis into... Yeah, so that's false. 17 is false. 18. The correspondence between XB and B is called the coordinate mapping. Okay, so X to XB is called the coordinate map. What was the problem? So this is false. 18 is false. 19. The vector spaces P3 and R3 are isomorphic. That's false. 20. In some cases, a plane in R3 can be isomorphic to R2. In some cases. Isn't it in all cases? I'm pretty sure it's all cases. All right, let's just double check here. I don't know if the book has all or just odd. I think it might just have odd. So the study guide has hints. I don't know where that's at. So let's just get ChatGPT to figure that out. Thoughts on solving complicated integrals? Do I find it fun? No, I don't find it fun, honestly. Not really. I just feel like since we have these massive tables and algorithms that do like stuff that we could never really do, like stuff with like these not just error functions, but that what are they called? Not hypergeometric, but there's all those like I think it's called the Fresnel function or something like that. There's all sorts of like crazy non-elementary integrals that like you could do on a computer that you would just not do by hand. So no, I don't really find them fun. All right, 15. 15 is true, 16 is true, 17 is false, 18 is false, 19 is false, and any two-dimensional subspace is isomorphic to R2. Okay, so true. All right, so those were easy. All right. All right. All right, so we've got 1, 2, minus 3, 1, minus 3, minus 8, 7, and 1. So, all right, this is really B. That's what I should be calling it, but whatever. Yeah, what happens if I just do this? Right, but that doesn't give me all of them. Is that always the case, though? That any pair? I don't think that's true. That any pair. Here, let me just talk to it. Like in this case, the dimension of the space is R2, but we have 3 vectors in R2, but it's not always the case, right, that any 2 vectors in our set of vectors is going to span the space, right? Yeah, because just imagine that we have a copy. Like imagine it was 0. Imagine this one was 0 and then you have these two, then obviously this one is useless. So then if you took this and this, it doesn't necessarily mean that you can get there. It doesn't lie on that line. But in this case, it just happens to be that for any pair, you can. Yeah, right. That's an interesting question. Right. It just means that they're linearly independent. Yeah. Yeah, and more generally, then any trace of n of them is a basis. Okay, cool. All right, so that makes sense. All right, 22. Let B1 to Bn be a basis for B. Explain whether B coordinate vectors. Okay, so we already did this one. This one's obvious because it's like, okay, so we have B times some xb is equal to x. That's like our general formula for this stuff. And explain why the b coordinate vectors of... Okay, so let's just say that we're trying to write... So we have b1 dot 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 bn times x, or we'll say this is b1 under b is equal to b1. Okay, so we're gonna have... So imagine that we have like b1 dot 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 bn. Okay, times xb is equal to b1. Okay, so this is going to form a basis. So now we just take a random matrix, then we're going to take b1 equal to b like this, the first column, and now we're going to try to find b backslash b1, and we're going to get 1 0, and then if we do this similarly for b2, you get 0 1. So because if we have like a b c d times x y is equal to... Here, let's just see, do we have a b b... Here, let's just do all right, something like that. I'm just gonna write down on paper. So then you get ax plus by is equal to a... You're trying to get a the first column. So yeah, it's gonna be xy is gonna be 1. It's gonna be... So yeah. Okay, and then you're gonna get cx plus dy is equal to c. So then you're gonna get okay. I think I get it. So problem 23. Let S be a finite set in a vector space V with the property that every x in V has a unique representation as linear. Okay, so what do we have? We have that for all x and v, there exists a unique, let's call it an xb, such that the linear combination of xb with the elements of s equal x. If suppose that it wasn't unique, then this would be linearly dependent. But it is, so it's linearly independent. And it spans the space. All right, let's see how ChatGPT is going to answer it, because I feel like I just answered it. Okay, so yes, we need to say it spans V and it's linearly independent. So by hypothesis, every V admits some linear combination. That is the definition of span. Perfect. And then linearly independent. Yeah, and I did the same thing, the contradiction. Suppose that it was great. That's what I thought. Okay. 24. Suppose that V1 to V4 is linearly dependent spanning set. I'll skip that one. That one's boring. Okay, all this stuff is just inverses and stuff like that. Maybe we'll just do 27 and 28. These are both just B inverse. Okay. Just have this do it. Okay, so let's just say B. So for 27, we let B equal the map. We have B times XB is equal to X, right? And B is a basis, so we get we hit everything. Now we want to show. The thing is, what's weird is that X. So, but B inverse is the right. Isn't P or P inverse, whatever it's called, the mapping from X to XB is going to be. Where do they describe that P inverse thing? Okay, so so P inverse is the coordinate mapping. So B inverse we're gonna call as the coordinate mapping that goes from X to XB. Okay, so now we're assuming that that okay, so we want to show it's 1-to-1. We suppose for contradiction that UB is equal to WB. Okay, but um, if we apply the change of coordinates to the standard basis by multiplying both sides, multiplying both sides by B, then we're going to get U is equal to W, right? Pretty straightforward, I think. Okay, let's see. So it's a basis. So every X and V can be written. Hey, what's up? Linear algebra, bruh. We're doing linear algebra. We're almost done with this section. We're going to move on to change of basis next. Um, Okay, so oh, is that really true? If the dimensions of v and w are equal and not infinite, then if you have injectivity, you get surjectivity and thus invertibility. Wow, that's kind of cool. That's really cool, actually. All right. Okay, I think that's it for coordinate systems. All right, nice. That only took an hour. That was good. All right, I'll be back in a minute.